We're going to take a look at 3 questions from our homework last night, worksheet number 8. The questions that we want to see are 5, 6, and 8, starting with question number 5. Calculate the magnitude of the electric field experienced by an electron if the net force experienced is 6.5 times 10 to the negative 16 newtons. There is an electric field experienced by an electron. Is that electron producer or experiencer? Tells us right there, right? It's experienced by an electron. But even if you don't touch that, listen, we know the electron is at that point, so we know it's got to be an experiencer. Now, there's going to be a producer over here somewhere, but we don't really care about that producer. We don't know anything about it. Let's just use the experiencer data. We know the force that it experiences is 6.5 times 10 to the negative 16. We know the charge of the electron, it's on our data sheet, it's 1.60 times 10 to the minus 19 coulombs. Isn't that negative, though? Isn't the charge of an electron negative? Yeah, it is negative, but it doesn't matter here because we always drop the sign of the charge when we put it into an equation, right? So what is 6.5 divided by 1.6 times 10 to the minus 19? We get 4.06, 4.06 times 10 to the 3, and the units would be newtons per coulomb. Good. All right, number 6 was it? Okay. Calculate the magnitude of the electric field experienced by an alpha particle. The net force is 2 times 10 to the negative 16. What's the initial acceleration? So almost the same question, but a little bit more. Okay, we want to find the electric field. Similar question here. We have an alpha particle experiencing this field. We're going to say that E is equal to F over Q. F is 2 times 10 to the negative 16. And the charge of the alpha particle, where do we find that? Yeah, go to your data sheet. When you do, you find that it's 2E, 2 times the elementary charge, or 3.2 times 10 to the minus 19 coulombs. We do the math there, works out to be 625 newtons per kilogram. Sorry, newtons per coulomb, I should say, for my electric field strength. Now, you want to find the acceleration. Hey, what are we going to do 99 times out of every 100 when we're looking for an acceleration in physics 30? There's lots of equations, right? But 99 times out of 100, we're going to use the same one. Which one is it? We talked about this before. We've used it before. F equals ma. F equals ma. Okay, you got force here. Solve for A. F is 2 times 10 to the negative 16. And M is what? The mass of an alpha particle. It's on our data sheet. Do the math there, what do you end up getting? Pretty big number, right? We say meters per second squared, or we could say newtons per kilogram. Either one of those works. Don't forget that. Listen, there's lots of things that we do in Physics 30 that are hard. Lots of things that you've really got to think hard about. This is not one of those things. When you're asked for acceleration, get a force. Whatever force happens to be appropriate, and then divide it by mass. That's it. Okay, that's a recipe. Okay, that's as easy as, you know, going home and getting this ridiculously simple recipe for making Jell-O. We follow the recipe. It works every time. We don't have a lot of recipes in Physics 30. We got to think a lot in Physics 30, a lot more than we did in Physics 20. But this is one of those situations when you're looking for acceleration, take the recipe. Okay, make your Jell-O and walk away with the correct answer for a question. Okay, let's nail those questions. Take the gimmies. Okay, there's no such thing as a gimme, but take the questions that are almost gimmies and nail them. Okay, lastly, question number 8. 2 charges in a straight row. First charge is 5 times 10 to the negative 5. Second one is negative 2.5 times 10 to the negative 5. And we want to find the strength and direction of the net electric field midway between. So we want to find the field strength right there and the direction right there. The distance is going to be what, 0.025 meters? Because it's halfway in between, 2.5 centimeters. No, that's wrong, isn't it? 2.225. All right. Which way is the field caused by the positive? To the, listen, which way does, we define the direction of the electric field as away from the positive and toward the negative. So if we're looking at this one, the field caused by this one, it's going to be to the right, away from the positive. If we're looking at the field caused by this one, it's going to be to the right, toward the negative. They're both to the right. That makes sense? We got to catch that, right? If we have a positive producer, the field will always go away from it. A negative producer, the field always goes towards it. This one's good because both fields are exactly the same, in exactly the same direction. Let's find E1, KQ1 over R squared. What did I get for E1 there? 8.879 times 10 to the 8. We'll say newtons per coulomb for that one. Now we're going to say E2. This is one we could actually, if we really wanted to do in our heads here. I'm going to say it's 4.4395. Is that right? Times 10 to the 8. How do we get that so quick? Yeah. Yeah, since all the numbers are the same except this is half the value of the other charge, we just took this number and divided it by 2, right? This wasn't, oh, let me multiply K by Q by divided by R squared, and lo and behold, we end up getting this number. It was taking the answer from the previous one and simply dividing it by 2 because the charge was half the charge. Now, they're both in the same direction, so now what we're going to define the net field here is simply add them up. We're going to say 8.879 times 10 to the 8 plus 4.4395 times 10 to the 8. Okay, whatever we get there. Good? If they were in opposite directions, then we'd have to make one of them negative. All right? You guys have any questions with the practice problems that we had on page 550? No? All right, we're going to go through a number of multiple choice questions with you guys today, starting with question number 44. We'll give you about 30 seconds to see what you can do with 44 on your desks, and then we'll take a look at it as a group. Okay, 44, the types of charge present on X and Y are. Forget about the options here right now. Let's look at the picture, and I want you to tell me what you know, first of all, independent of the direction of this field. What do you know about these two charges? They've got to be the same, right? They've got to be the same. Why? Maddie, how do you know they've got to be the same? Yeah, the lines are not joining up. Okay, if the lines join up, it's an attractive force. If they go away from each other, they repel each other, then it's got to be a repulsive force. And if we've got a repulsive force, then the charges have to have the same value. Now, both positive, both negative, we're not sure until we look at the direction. So, the answer is going to be either A or D as a result of that, though. Which is it, A or D? Are they both negative or are they both positive? Both negative, both positive, Maddie? Why do you say they're both negative? Yeah, so we're looking at the shape of it, and we're also looking at the direction of the arrows pointing towards the field, the particles, so therefore they're going to be negative particles. Yep. All right, so it's going to be opposite of that. Yeah. All right, take a look at number 46. Okay, let's have a look. It says two particles, 1 and 2, of equal mass of opposite charges. And we can see that from the picture, right? One's positive, one's negative. The negative charge on particle 1 is 3 times greater than the positive charge on particle 2. Let's call particle 2 Q, and let's call particle 1 3Q, because it tells me it's 3 times the charge on particle 2. Particles are 9 centimeters apart. We want to find the electric field strength midway between the two. So we're going to say the distance is 0.45, no it isn't, 0.045, right? 0.045 meters and 0.045 meters. Now let's look at the direction of the field caused by particle number 1. Okay, this is negative. The field points toward the negative. We'll call that E1. Now this one's positive. The field points which way? Away from the positive, so to the left. We'll call that E2. So they're both to the left. Which way is the net field going to be? To the left, yeah, to the left. Now, what if one of them was to the right? What if this was a negative particle? It's not, of course, but what if it was a negative particle to the right? Would they cancel each other out? Give me a net field of 0. Jesse, why wouldn't they cancel each other out? Okay, so that's going to be a bigger field. The net field is going to be to the left, but how much to the left? Well, we could figure that out, actually. Hey, what the proportions were. We could say that E1, actually, let's say E2. E2 is KQ over R squared. We would say that E1 would be K times 3Q over R squared, which becomes 3 times KQ over R squared. In other words, E1 is 3 times the value of E2. Got it? So this one would be about 3 times bigger than the value of E1. So the net field would clearly be to the left in there. Okay. Let's try another one. This one is number 50. Have a look here. The intensity and direction of the electric field produced by an alpha particle is what value? What's an alpha particle? We don't actually learn until our last unit, midway through our last unit, sometime in December, what an alpha particle really is. But we don't really need to know what an alpha particle is right now. We just need to be able to find out data for an alpha particle. And we can get that from our data sheet. On our data sheet, we know that we can see that an alpha particle has a charge of plus 2e, 2 times the elementary charge, and it has a mass of 6.65 times 10 to the minus 27 kilograms. Okay, the charge is all we need for this question. The fact that it's positive, and we want to find the field strength a certain distance away from that. Which way is that field going to point, by the way? Left or right? It's going to point which way, Jesse? It's going to point away from the positive producer, right? So we know the answer is going to be either B or D as a result of just the direction. What about the magnitude of it? E is equal to KQ over R squared. Okay, we got the value of Q, we got the value of R, and I think when we do that, we end up getting D, don't we? 1.2 times 10 to the 12th. There we go. Yeah, I'm going to create a couple follow-up questions to this. Okay, questions that aren't asked here right now. Get rid of this because all the follow-up questions have to do with direction. What if I was to put there's nothing there to experience that field right now, right? So no force, but there is a field, just no force. What if I was to put a positive particle right there? What would happen to it? It would experience a force, Ethan. Same direction as the field, right? We know from the definition of the direction of the electric field that a positive particle experiences a force in the direction of the field. If I was to take that positive particle away, that doesn't change anything about the field. Okay, it still points to the right. We just know that if there is a positive particle there, it's going to go in the same direction as the field. What if I was to put a negative particle there? Which way would it go? Which way would it experience a force, I should say? To the left or right? To the left. It's going to experience a field force opposite to the direction of the field. And we know that because it's attracted to that positive producer, right? What if I do this, though? What if I leave the field there, but I hide what causes the field? I mean, clearly something must have caused the field, whether it's a positive producer over here, or whether it's a negative producer over here, or some kind of combination of both. Something must have caused that field, but we don't know what it is. We know there's a field to the right. If I didn't put a positive particle in that field right now, which way is the force on that positive particle? To the right, because positive particles experience a force with the field. What if I were to put a negative particle in that field? The force is to the left. We don't know whether it's a positive particle here that it's attracted to, or whether it's a negative particle here that it's repelled by. Doesn't matter. We know that positive particles experience a force with the field and negative particles experience a force against the field. That make sense? That's okay? Here's one for you, though. What if I create a field that looks like this? This is an electric field caused by whatever. Big positive up here, big negative down here, whatever, doesn't matter. Big field like this. And I put a positive particle in that field, and I send it through to the right, perpendicular to that field. What do you think is going to happen to it? Which way does it experience a force? Downward, in the same direction as the field, right? Because positive particles experience a force in the direction of the field. But it was already moving to the right. So it's moving to the right, experiences a force downward. What happens to it? It ends up kind of curving downwards like this, right? What's the shape of that path called, do you know? What is it? It's a parabola. What is this like? What does this remind you of? Well, okay, math, okay? It's projectile motion from physics 20, isn't it? Okay, in physics 20, we had masses going through gravitational fields following a parabolic path. Now in physics 30, we have charges going through electric fields. It would follow a parabolic path. We'd analyze it in the same way as we do projectile motion, except that A would not be neg 9.81. A would be some other value, depending upon the strength of the electric field. Does that make sense? You're probably not going to have to analyze a problem like that, but at least you know if they want it to be you-know-whats and throw a question like that out at you, at least you'd have some kind of fighting chance as to where to start with it, right? Yep. Let's try another one, number 51. Okay, let's have a look. So the magnitude of an electric field at a distance x from a point charge is 8.3. The distance is increased to 3x. The charge is reduced to q over 4. What's the new electric field become? What kind of question is this? Besides the electric field, right? Clearly it's the electric field, but what's the technique that we're going to use to solve this? You guys remember what we call it? Even if you don't remember what we call it, but remember how to do it, that's fine. Ready? Yeah, it's the variable value changing thing, right? We're going to say we have a producer here. This producer produces this field. And we're going to say that electric field, the original electric field, is equal to kq over r squared, but it's also equal to 8.3 times 10 to the negative 4. We're going to say the new electric field, after we make our changes to it, is going to be k times what? Q is now 1/4 of what it was. And r, the distance is, well, if it was x, now it's 3x, or if it was r, now it's 3r. We got 1/4 kq over 3 squared is 9. That's the same thing as saying 1/4 times 1 over 9, right? 1/4 divided by 9 is the same thing as saying 1/4 times 1 over 9. So that becomes, well, 1 over 36 times my original electric field, 8.3 times 10 to the negative 4. And when we do that, I think it works out to be C or D. What is it? C? D? 2.3 times 10 to the negative 5. Did you get it?
Well, like, I think
one more question, last one, number 52. All right, let's take a look at this one now. Where do you want to start? Who's got an idea here? Dylan, you know where to start on this one? Okay, so what did you do with the horizontal ones? Okay, so did you draw a picture, a diagram? Okay, so if we make this the blue one and this one the green one, the field caused by the blue one is going to point to the right because it's away from the positive. and the field caused by the green is going to point to the left because it's away from the positive. And because those numbers are all the same, they're going to cancel each other out, right? Okay, that makes life a lot easier for us, right? Because now we've got a one-dimensional problem. I'm going to just kind of scratch these out, pretend they don't even exist. They do, but since they cancel, it's as if they don't even exist, right? Good, good, good observation. All right, let's do the same thing for the other ones and see what happens there, okay? Okay, it doesn't look as much like these are going to cancel out, but let's give it a whirl here, okay? Green one and blue one. The electric field points away from the green one because it's positive, and it points toward the blue one because it's negative. Now, I've got them drawn at equal lengths, but we don't know what the values of these electric fields are, so we should figure them out, right? We're going to say E1 is KQ1 over R squared. We're going to say E2 is equal to KQ2 over R squared. Now, I don't know what the values of both of these work out to be, but I do know that whatever it is, it's the same. If these two things are the same, E1 and E2, but opposite directions, what do we know about them? They cancel out as well. So what's the net electric field if the left-right cancel and the up-down cancel? How many people got D for that? 0? Good. Good. That's a challenging question, actually. As it turns out, it turns out to be pretty straightforward, pretty easy, right? But it's just getting to that point of recognizing exactly what to do with it.